All right, good afternoon, and welcome to our 3D biochemistry set of instructional videos on visualizing molecules. Today, I'm going to look at the protein structure and visualization and analysis using Chimera X, and we're going to analyze the structure of human hemoglobin, which is the oxygen-carrying molecule in humans and mammals and essentially every organism that has blood. And so we're also going to look at the structure with myoglobin as well. And so you're going to learn how to visualize a molecule in 3D as well as to maximize the information that you obtain from that, right? So the first thing we need to do is to obtain the structure of human hemoglobin, and so we're going to use the protein data bank. Now the website we have is sites.tntech.edu/biochem. That has all the text of the tutorials on here, so you can follow along. The tutorials are right up here. I've already opened our protein structure visualization and analysis using Chimera X. This was developed by Dr. Sean John and myself here in the chemistry department at Tennessee Tech. And so we're making it available for you. So the structure is available from the protein data bank. And so I'm going to launch this website here. The protein data bank is a fairly large database of 3D structures of proteins. There's 227,344 and growing structures in the PDB today. And there's also additional structures from AlphaFold which have been computationally predicted. We're not going to use those. We're going to use the actual experimental structures, but it's a fairly large database, and this is kind of the gold standard where you go for protein structure information, or even nucleic acids as well. Now everything in the protein data bank is indexed by a 4-digit search term, and so you can type that up here in the window. You can also just search for human hemoglobin if you want. I happen to know the code, and it's actually in our tutorial. I'm going to look for 6FQF. That's the 4-digit code. And that brings me to the structure of human hemoglobin. We know that's human because, of course, it says Homo sapiens. It was expressed in E. coli. That's the expression system they used for the protein, but it's the same sequence as human hemoglobin. And so this was deposited in 2018 by this group right here, right? Vergara and co-workers. We also know this is an X-ray diffraction structure, and because it tells us the method. X-ray crystal structures are kind of the de facto gold standard, if you will, for protein structures. And the resolution, essentially what we're doing in obtaining an X-ray crystal structure is you put the crystal in a you put the protein inside of a crystal, and that aligns all of the atoms in that crystal in the same direction. So you can get a consistent diffraction pattern where when, with X-rays, you get that diffraction pattern, and you can visualize the position of the electron density in the molecules. So most of these, carbon has 6 electrons on it, and nitrogen has 7 electrons in a neutral form. The one thing is that hydrogens are invisible to an X-ray structure because they only have 1 electron, so there's not a whole lot of electron density there. The lower the resolution, the higher the quality structure, and generally anything less than about 3 angstroms is considered to be a very good structure. The higher this number, then you start to get different parts of the protein that may have unresolved parts as well, so it's not quite as good. You can also see links to the literature in here. It tells you information about the protein, and you can download all these files in PDB format right here. The other way to access the protein database is directly through Chimera X, right? So we're actually going to do that. I wanted to show you the protein data bank, but we want to download. If you have not downloaded Chimera X yet, that's fairly easy to install. That's procedure number 1 right here. You obtain this from the resource for biocomputing, visualization, and informatics at the University of California, San Francisco. It's a free download. You can click right here and obtain the software. It ought to detect that I'm on a Windows system right now, but this is available for OS X as well as Linux. So once you install the software, then we need to run Chimera X. So you can just kind of go into your Windows or whatever operating system you're using and launch the software. Here's Chimera X coming up. And so when we first launch it, you're going to see an empty screen. You need to load a program. And so the 4-digit code is 6FQF. You'll see I've actually launched, I've already previously loaded it in my version here. But if you haven't done that, just type open 6FQF in the command line down at the bottom in the lower corner, in the lower left-hand corner. And that is the structure of hemoglobin. And so now we're visualizing this in 3 dimensions, right? So you want to familiarize yourself with the mouse that you're using, right? And I recommend using a 3-button mouse, just like this. You've got a left mouse button, a right mouse button. We also have a mouse wheel. You can actually see me as I use the mouse wheel. I'm zooming in and out of the protein, right? And so the left mouse button, when you press that, I've got to put it on a surface, but press and hold the left mouse button and you can kind of spin the molecule kind of like this, right? The right mouse button, if I press and hold that, I can translate in the same plane, so I can kind of move it around in this fashion, right? So you want to kind of visualize and get used to using the mouse in 3 dimensions. And then you can also press and hold. The mouse wheel is also a button itself, so you can press that button and there's additional functionality with that, right? So we're looking at human hemoglobin. You can kind of see the ribbons in the protein, and the ribbon represents the linear sequence of amino acids from the N terminus to the C terminus. What we also see is that we have a prosthetic group, and so you can actually see one of the hemes right here. And so that's the oxygen binding region in human hemoglobin, so we can kind of see that as well. And now what we notice is, well, first of all, I mean, this is a pretty big protein. There's actually 4 protein chains in here, right? And 2 alpha and 2 beta chains. And you can already see that there's 4 heme groups in here as well. Now, if you want to visualize the 4 chains of hemoglobin, we can color the ribbons by just going, we want to first of all go to select chains, hemoglobin chain A, and then we can go to actions, color, and let's just color chain A in lime green, right? Notice when I selected that, it kind of puts a little green aurora around the chain. So if I go to select chain B like this, now chain B has that green aurora around it, and then I know it's selected, so I can make chain B red, or whatever color you want, right? So if I select chain C, we can visualize that, select its color. Let's just make that blue. And let's select chain D, and we're going to change that color. We're in Tennessee, so we're going to make that a nice orange color, right? Go Vols, right? Anyway, so Now we've colored the 4 chains in different colors, but also it colored the atoms the same color as the chain. Now, what we can do is change the heme group atoms, and if I deselect, I just press and hold the control button and press anywhere in the background, and that will deselect whatever you previously had, right? So that's also kind of useful because then you can select a new selection. And if you're deselected, then whatever you do would be, whatever command you execute will be applied to the entire molecule, right? Now let's visualize the atoms of the heme groups down here in their CPK coloring scheme. So CPK stands for Corey, Pauling, and Coltoun. That CPK coloring was designed to visualize in molecular modeling, to visualize and recognize the atoms by their atom type using simple colors, right? So if I go down here to add actions, color by element, now all the heme groups are colored by their CPK colors. So carbons are gray. You can kind of hover over here, and that'll tell me that this heme carbon, this is a heme carbon in chain D. That's gray. That's because it's a carbon. This blue atom, that tells me that's a nitrogen. This red color over here, that's an oxygen, so we see an O. And it says O2 because it's also numbering the atoms, right? So like this nitrogen is NB, because that tells us, you know, that's Na. So it kind of has its own scheme, NC, ND. So they're all nitrogens. And then this is O2D, O1D, right? And then down here we have O1A and O2A. Then we have kind of a pink atom in the middle here. That's the iron, right? So that's the heme iron. We also notice, one other thing, if we have any hydrogens, hydrogens are also in white. We haven't added any hydrogens, and this is a crystal structure, so hydrogens are invisible. You will notice some extra atoms, like if we kind of look here, hover over that, and that tells me that's HOH 329O, so that's an oxygen, and HOH tells me that that's an H2O molecule, right? Except there's no hydrogens because when we obtained the crystal structure, it detected a water molecule there, but it couldn't see the hydrogens, so that's basically a crystallographic water. We also see a water molecule here as well, which is actually bridging an interaction between this histidine and the heme group. So that's actually fairly significant. So sometimes bridging these waters are actually significant to the structure, right? Now if we want to add the hydrogens, I can just kind of go to Tools, Structure, Editing, Add Hydrogens, and it's going to take a minute because it's adding hydrogens to the entire molecule. There it goes. Now I've got hydrogens present, and look at that. Now we have some water molecules that are present right there, right? So that's how to kind of visualize with the hydrogens added, right? Now the one thing we've got 4 chains in hemoglobin, and not all of them are, well, I mean, we've got 2 alpha and 2 beta chains. The heme groups are essentially identical. There's some slight differences between the alpha and beta chains, but we're going to focus on mainly one chain, just for the sake of simplicity, and then obtain all of our measurements and calculations from that one chain. So in order to take away the other chains, again, I'm going to go to Select, and I'm going to select chain B. Well, this is actually chain D. And using the toolbar, I can hide the atoms and hide the ribbons, so chain D is now disappeared. If I select chain C, I can do the same. I can select chain B, and I can do the same as well. So now chain A, colored in green ribbons, is the only one visible, and I can kind of rotate around so that I can see mainly the heme group atoms right here in the front, right? You'll see I've got about 4 or 5 water molecules. Many of these are right in the front. Now, if I want a clear, unobstructed view, you know, sometimes this water might kind of get in the front. So what I can do is if I press down Shift and Control, I can then select all the atoms of these water molecules. Now, if you don't press the Shift key as well, then when you select the second atom, the first selection will disappear. So in order to select all of the atoms in your selection, we need to hold down Shift and Control at the same time and select all the atoms so they're all selected. Now I can make these waters disappear. Notice I did not make the other water disappear behind here. There's actually another water back there. I didn't. But that's also bridging an interaction. But this water right here, this water 306, is bridging an interaction between the heme group and the iron atoms. So that's actually fairly significant. So I don't want to make that go away, right? So that's essentially how to visualize an interaction, right? And so let's just kind of look at our little guide. Let's go back to here. So we've downloaded the structure from the protein data bank. We're visualizing only chain A, as it says in number 3. Number 4, we want to locate the histidine 92 and 63 residues in the protein, because these are both very significant because they're involved in oxygen binding and heme binding, right? Now the best way to do that is to use the sequence viewer. And so if I go to Tools, Structure, or Sequence Viewer, Show Sequence Viewer, I just want chain A, and my sequence will appear. This is the sequence with the 1-letter amino acid codes appearing at the right in my console window, which kind of has a, this has a running, thing of our commands that we're executing. So that's actually fairly useful. Everything we've done kind of shows up in the sequence editor. So here's the 1-letter codes, and so we kind of go from 1 to 146. I want to find histidine 92 and histidine 63, and if you kind of hover over it, there's proline 58, so histidine, there's histidine 63, and then I can select it here, and when I selected that, notice that histidine 63 also has a little green aurora over here. And then press Shift and Control at the same time, and let's find histidine 92. There's histidine 92, and let's select that. So now both of my histidines are selected, right? Now if I want to label these, so we can find them, let's go to Actions, Label, Residues by Name and Number, and now we've got histidine 63 and histidine 92 selected, right? So there are 2 histidines. We've identified them. We've labeled them by name and number. We've identified the heme. We can look at the water molecules in the protein. We've added hydrogens. That's number 7. And then to visualize the hydrogen bonding in the protein, we can go to Tools, Structure Analysis, Hydrogen Bond, and select our molecules, right? And so we want to select histidine 63 and 92 and the heme, right? So these are already selected, and then I want to just select the atoms of our heme, right? And then let's select this water molecule as well, right? Now let's go to Tools, structure analysis, H bonds, and so now let's go ahead and select. And that selected all the hydrogen bonds in my entire protein. Look at that. So that's going to be kind of hard to see, right? So let's just kind of go back and we will select the chains again. So chain D, we're going to make that go away, right? Then chain C, we're going to make that disappear. Chain B, we'll make that disappear, right? But, you know, now I also have all the other atoms. Now, one thing you'll notice is all the hydrogen bonds appear with little dashed lines throughout the protein. We also see some dashed lines in our alpha helices as well, right? Now, some of these water molecules we can disappear because we don't need these. Here's a water molecule interacting with the heme. Now I can also kind of select these. I think now I selected part of the protein, so just kind of select the atoms themselves individually, like so. Now, sometimes what you can do is use the lasso tool to select other things, right? So we can select that water, and we'll select that stuff. If I use the lasso, I'm going to get part of the protein. I don't want to do that, right? So, but I can do that. I can select this water right there, like so. And then we just hide those waters, right? So now they're disappeared. So now I've got, we see it. Let's look at histidine 63. And we can see clearly we have a hydrogen bond between this nitrogen and the oxygen, right? And then we also see another complex bond between the water oxygen and the iron atom, right? So we kind of see a little bit of both right there. Now this isn't a hydrogen bond because hydrogen is not involved, but it is still detecting that as an interaction. We also see another complex bond below, right? So all the hydrogen bonds are visible. Now if I want to measure the distance of this, right, I think the next thing we see under number 9 is measuring distances, right? So we can use the structure analysis tool to measure the distance. And I have to select both atoms. So if I want to select this oxygen and this nitrogen. Now when we're measuring a hydrogen bond distance, because hydrogens are invisible to crystallographers, and that is the gold standard of protein structure determination, we always measure a hydrogen bond distance from the heavy atom to the heavy atom. We never measure to the hydrogen, even though these blue lines go between the hydrogen and the heavy atom. We're going to measure the hydrogen bond distance between the two heavy atoms. That's just standard. And so I go to Tools, Structure Analysis, Distances. Now my distance toolbar here appears, and I've got the two atoms selected, so I just click Create. And it looks like I got an error because you need only 2 atoms selected, and I think I selected an extra atom somewhere. So just go ahead and press Control and press on the outside to make sure everything's deselected. Just press on the black area. Now hold down Shift and Control and select both atoms. Now select my hydrogen bond, and that's 2.462 angstroms is what it selected it as. And then what I can do is again press Control and just press out here to deselect. And let's measure the distance between the oxygen and the iron. And that's 2.187 angstroms. And now let's press this distance and that's 2.115 angstroms. So that's how we can measure the distance. You can measure the distance between any atoms in the molecule, right? Now, if we want to obtain a picture of this, right? Now, the first thing, if we get a picture, we want to make sure and orient the molecule so that we visualize kind of mainly what we're interested in, right? And you know, if I we also want it to be zoomed appropriately. If I take a picture of this, it's kind of hard. Everything's really small, right? So I recommend kind of zooming in so that we highlight mainly where we're actually interested, right? And make sure there's nothing in front, right? So I'm interested in these histidines as well as the heme group, right? And I want to get an appropriate level. So if I want to take a screen capture of this, now you could take a screen capture with the snipping tool, but that will take it at screen resolution. We can actually go up here to save and save a PNG file and just call this hemoglobin, whoops, histidine heme, for example. It'll put a PNG extension. I'm just going to put this on the desktop, and that saves my image. Now, the one thing you'll notice, if I print this on a black background, and if I'm going to print this in like a journal or something, that black will just eat up printer ink. So I recommend going to Actions, Color, All Options, and selecting Background and changing the background to white. And then, and of course I also had an extra character in there. So here's my white. So now I've selected my white. And then my hemoglobin right here, here's the PNG image file. And that's my picture that I've got saved as an image file, right? So that's how to look at hemoglobin, and we've kind of analyzed the hydrogen bond distances there, right? Now the next thing, let's see, we've looked at distances, we've generated a figure, we can save the snapshot, right? And so now the next thing to look at is the segment of the alpha helix, and so this segment we want to look at is asparagine 80 to lysine 95. The easiest way to do that is go back to our sequence viewer and to select residues 80 to 95, right? Now the one thing, if we're going back, notice we have a white background, and if we're doing some work, that white is going to cause eye strain. So I recommend going back to change the background color back to black to minimize eye strain. That's going to just make things a little bit easier to work with, right? And now let's go and hide all these atoms, right? I'm going to make the heme appear again. So I go to residues, select HEM, and then let's make the hemes appear. Notice when I did that, it thinks all the hemes are part of one. So again, what we can do is we can just kind of use the lasso tool, select all the hemes except for the one inside our protein, and then we can visualize the heme. Now, in our chain A, so here's my sequence viewer again. There we go. Let's make this go away so we can get it a little bit larger. So I want residues, which residues did it say again? So, and then histidine 92 shows up again, right? So what we can do now is we can kind of look at this alpha helix a little bit more closely, right? And alpha helices are very ordered. The first thing we see is all of the hydrogen bond networks in the alpha helix, right? And so each one of these is a hydrogen bond between the NH of the backbone and the carbonyl of the backbone, right? So we've got a very ordered structure. Now to visualize the backbone, I'm going to make the things go away a little bit, and then that way we can kind of see that where our hydrogen bonds are, they're very ordered between the NH and the carbonyl of our amide bonds. That's between our peptide bonds right there, right? And then we see all the side chains as well, right? So, and then I can kind of, well, I guess what I shouldn't have deselected that because I want to put the ribbons on again. Now what we can kind of do is we can kind of look at how many residues is in a complete turn of the alpha helix. So if we go from here, we turn around, and then this is one complete turn right from, what's this? That's the aspartate 94. That might be a little bit further out from the alpha helix. So let's see, what's the next one? That's cysteine 93. And if we go to turn one complete turn, that goes to glutamate 90. We could even maybe go to serine 89. Well, that's going to be about 4 amino acid residues, right, in this complete turn. Now, in your biochemistry textbook, we use Garrett and Grisham, but most biochemistry textbooks will tell you that the number of residues in one complete turn is about 3.6. And so if there's if I'm counting roughly 4 amino acid residues, well, I'm not getting the exact turn, but I'm getting pretty close to 3.6, right? Because these, I think this aspartate 94 is a little bit beyond the turn. Some of these are, this one right here is glutamate 90 is a little bit before the turn. So we have roughly 4 amino acid residues, or 3.6 in one complete turn. So you can kind of look at that, and you can then determine, hey, this kind of agrees with what's published in the textbooks. Similarly, you can also look at some of the other numbers as well. And so I think, where do we have this in the structure? Yeah, I think it's number 15. Can you determine the number of residues per complete turn of the alpha helix, as well as the rise per residue and the rise per turn? So those are questions we can ask by looking at the structure. We can also save a snapshot the same way we did before. Again, I would try and change the background to white for printing. And then the last thing we can do is we can compare the structure of chain A with myoglobin. Now, myoglobin is analogous to hemoglobin, but there is only one chain in myoglobin versus 4 chains in hemoglobin. They both carry oxygen, but myoglobin is in muscle that accepts the oxygen from the hemoglobin. And so the structure of myoglobin we have is 3-RGK. That's again from the protein data bank. And we can use Matchmaker to superimpose these structures together, right? So I'm just going to go ahead and hide. Oh, actually, I'm going to visualize the ribbons, but I'm going to hide all those atoms and then deselect. There's chain A. And let's open, I type open 3-RGK. And there's myoglobin in a nice purple residue right there, right? You also see myoglobin has a heme group. So there's the structure of myoglobin. We did have a couple phosphates in this crystal structure as well. We can actually select those phosphates. I want to select just the phosphate. Let's just hide that atom. We've got another phosphate in here. We can hide that. We can hide, oops, there we go. Select the oxygens, get those out of the way. Those are just waters. And I'm just going to kind of make this go away as well too. Right, so hide those. And so there's myoglobin. Now these two are not aligned. So let's go ahead and align those. And we're going to use the matchmaker function. We can go to Tools. We're going to go to Structure Analysis and Matchmaker. And so what we need, we've got a reference structure and a structure to match. We want the reference structure is my hemoglobin chain A. My structure to match is my myoglobin. I do want to restrict just to selection because my reference structure does have 4 chains in it, and I only need I only want it to align to chain A, so we don't want to confuse it. So let's just go ahead and select chain A and restrict to selection. Make sure this checkbox right here is checked, right? And then we're going to get the best aligning pair of chains. We're going to select OK. And now they're aligned. And let's just kind of look to see. I've got the heme. Let's put the heme kind of in front so we can see them. There we go. So my hemes are aligned and my proteins are aligned. And actually it looks like a pretty good structure. Now to quantify this, we're going to look at the root mean squared deviation, right? That's the RMSD. And so that's this value that it gave me, which it told me is 1.074 angstroms. So what it's doing is it's aligning all the atoms in the molecule. And I think this is doing a heavy atom alignment, so it's not taking account hydrogens. Of course, there's no hydrogens in the myoglobin structure. And it aligns them. Now, if the RMSD if the alignment is perfect and all the atoms are in the same place, the RMSD will be 0.000, right? Or just 0, I guess. And the higher the RMSD, the more divergent the two structures are. So 1.074 is actually a very good alignment, right? And so it aligned this very well. Now it aligned it almost perfectly, but the one thing we notice is if we kind of look at the sequence viewer for myoglobin, the sequences don't match perfectly, right? Remember, hemoglobin goes from 1 to 146, myoglobin goes from 1, and in this structure it's 149, and then it's 153 residues, but these 3 are not there in myoglobin. So myoglobin's a little bit longer in amino acid sequence than hemoglobin, but it's still fairly close, right? So that is essentially how to align it. And then if we wanted to get a picture of this alignment, we can change the background. We can also do a spin movie. That's kind of neat. And this saves an MPEG of the rotations around the molecule. So rotating. Now it's generating my MPEG. And so that will save an MPEG, right? And so that saves it in my downloads directory. Then I can actually look at that if you want to do a spin movie. So that's something else we can do, right? So that is essentially how we've analyzed the structure of human hemoglobin.